because of that, when we talk about resolution, I want to introduce a term which was coined by Ernst Abbe, I just showed. So that's called numerical aperture. And why, in camera, there's an aperture. And that's those who like to have a taking photography, you can also understand. So you have a smartphone that has a lens that's a tiny, and that tiny lens do not provide us high resolution. But remember, some photographers, professional ones, will have a huge lens and take a very sharp image. And where comes that sharpness? Because this aperture is big. So that we call numerical aperture. More specifically, not only the absolute size of the lens, but from the object to the lens, this angle, halfway of this from the middle, this angle theta is 1 meter. The bigger, because of, remember the diffraction, this is kind of the maximum angle of diffraction which pass through this optical system, eventually focus down onto your film. So that angle is very important. And not only this angle, remember, if there is a refractive index medium over here, that can actually increase the effective information of diffraction here. So that we call n times sine theta max. Here is a theta max, and that's defined by Abbe. Hey, this is fundamental parameter which can decide the resolution of your optical microscope or image. So that he named as a numerical aperture. I'm not sure why he put the numerical, but it's not just absolute aperture size, but this ratio and that angle does really matter. Or maybe there's a refractive index n. Maybe this n comes from here. I don't know. But anyway, this is very important. And if you look at it, it's dimensionless because the refractive index is a ratio, non-dimension, sine theta is non-dimension. So then what's the important thing we have to understand for getting high resolution? So you see there's an aperture stop over here, physical elements, which is like iris, okay? So if you want to have high resolution, you increase this iris or aperture as big as possible. But if you don't need that, this means that there's enough of the information or light collection is happening. But what if you reduce down the iris? Like when you are in a too bright place, you want to make your iris shrink. In that case, in fact, you are losing your spatial resolution. So what's the meaning of this numerical aperture? And NA limits the optical information entering the imaging system. As I described you, the diffraction, the final information or final grading will diffract further, and that will be lost. So this numerical aperture is really about the optical information content which passes through your system. At the same time, the bigger this angle, the more information of diffraction, and you have higher resolving power or resolution. So in fact, I want to show how point will form an image on your image space. So let's say there's two cases, low and high NA. Low NA will form a tiny, let's assume tiny point formed here versus here. And in fact, this is not point anymore. It looks, I plot this one as a 3D. And if you look at under the screen or your camera, it looks like this, like disc with this shape. So that was discovered and named by Airy. So we call it as an Airy disc. So the size of a central disc really determines your optical resolution because tiny point become this disc. So the smaller disc here, you have high resolution that actually comes from high NA. So with the larger numerical aperture, you collect more light, and so you have a brighter image, and you have a better lateral resolution. But what are cons of this? Because of this high angle, you only can focus at the focal plane, but out of focus, you actually quickly lose your sharpness. So it will be blurred. So shallow depth of imaging with the maybe the other aspects of large NA, but it can be used by photographer that now have a nice picture, you have a nice focus at the object, but blurring out the other side. That can be artistically utilizable. So remember the tumor body, there's an n sine theta, and that n is refractive index of this medium. And that is related to resolution. To increase NA, you have to increase n from 1 to even bigger number. In the air, the refractive index is 1. But what if it's inside, immersed in the water, refractive index 1.33. What about in the oil? Then it's even higher. Refractive index is 1.52. So that you can even increase your resolution 50% of the time. So that's what I want to show. So that's where immersion oil is coming and it can increase resolution. And I want to show you why from this picture. So look at that. So this is microscope objective lens, and typically you have microscope slide and you have very thin, small specimen, and you have a regular microscope covered glass here. So what happens if there's a object for space is air versus, let's say, oil in this n equal 1.5 to 1. The rays coming from here, from the Snell's law, it will bend towards this way because this is a low refractive index compared to glass. Glass has almost 1.5 refractive index. So what happens is it bends towards the outside. And so this ray eventually turns outside of lens and you lose that information further. So this has a limitation. What if you fill this with an oil, which is matching refractive index, then actually this ray is now keep passing through until this angle. Because previously that angle is so high that they didn't even go through. That's why this one provides you more of a spatial information or spatial resolution. Hope that makes sense. So typical refractive index of oil is 1.515. So index matching is very important. If you are an aspiring cell biologist, you want to watch and observe a subcellular domain, which has a size of 1 micron level, then you have to use this high numerical aperture objective, and most likely you have to use immersion water or oil, okay, so that you can match and having higher refractive resolution. I want to just show you, this is cartoon, so this is reality. This is objective lens, and this is microscope slide. I think it's 1.2 millimeter. And in fact, this covered glass, it's not on scale. This is usually thickness of 170 micron. So that's like this thick, very, very small. And what about the distance of object lens to the specimen that we call as a working distance? In this case, working distance is only 230 micron. This is, you cannot even see very well with your eye. It's a very, very teeny tiny. And the most expensive part is objective lens. So you gotta be very careful when you do this high resolution optical imaging, because even small displacement in the wrong direction can break your sample, and even worse, break your objective lens too. Okay, so hopefully, so the rule of thumb is, in practice when you do experiment, you go to as close as possible and then only move the other direction to find the focus. That's a practical tip. So how to increase numerical aperture to improve resolution? So if you can increase resolution, you need to increase numerical aperture. So people have thought how to increase. First, you want to increase this angle, which means you have to have a bigger lens. Okay. And the other is you need to use this medium as a higher refractive index, such as oil in this case.